the set of models is non-empty. Okay, so it's not self-contradictory, in other words. So now we can reduce ask and tell to satisfiability alone. Okay? Remember, ask and tell have 3 possible outcomes. If I ask a satisfiable question, how many possible outcomes are there? 2. So how am I going to make this work? I have to probably call satisfiable twice. Okay? So let's start with asking if knowledge base union not F is satisfiable or not. Okay? So if the answer is no, what can I conclude? So remember, the answer is no, so it's not satisfiable, which means that KB contradicts not F. And what is that equivalent to saying? Sorry?
At that point.
Yeah, so it's not F. So it's, which one of these should it be? Entailment, contradiction, or contingency? Yeah, so I'm interested in the relation between KB and F. I'm asking the question about KB union not F. Yeah?
If F is already in KB, if try to add not F, that's a contradiction. It should have F and not F.
Yeah. So, exactly. So this should be an entailment relation between KB and F. Remember, KB entails F is equivalent to KB contradicting not F. Okay? Okay, so what about if it's yes? Then I can ask another question, is KB union F satisfiable or not? So if the answer is no, then what should I say? It should be a contradiction. Because, I mean, this literally says KB contradicts F. And then finally, if it's yes, then it's contingency. Okay? So this is a way in which you can reduce answering ask and tell, which is basically about assessing entailment, contradiction, or contingency, to just at most 2 satisfiability calls. So why are we reducing things to satisfiability? For propositional logics, checking satisfiability is just the classical SAT problem, and it's actually a special case of solving constraint satisfaction problems. And the mapping here is we just call propositional symbols variables, formulas constraints, and we get an assignment here and we call that a model. So in this case, if we have a knowledge base like this, then there are 3 variables, A, B, and C, and we define this CSP, and then we can, if we find a satisfying assignment, then we return satisfiable. If we can't find one, then we return unsat. Okay. So this is called model checking. It's called model checking because we're checking whether a model exists or is true. So model checking takes a knowledge base and outputs whether there's a satisfying model. There are a bunch of algorithms here which are very popular. There's something called DPL, named after four people. And this is essentially backtracking search plus pruning that takes into account the structure of your CSPs, which are propositional logic formulas. And there's something called walksat, which is, you can think about the closest analog that we've seen is Gibbs sampling, which is a randomized local search. Okay, so at this point, you really can have all the ingredients you need to do inference in propositional logic. So you define what propositional logic symbols are, or formulas are. I define the semantics, and I've told you even how to solve entailment and contradiction and contingency queries by reducing to satisfiability, which is actually something we've already seen coincidentally. So that should be it. Okay. But now coming back to the original motivation of x1 plus x2 equals 10 and how we were able to perform that logical query much faster, we can ask the question now, can we exploit that the factors are formulas rather than arbitrary functions? And this is where inference rules is going to come into play. Okay, so I'll try to explain this figure a little bit since it was probably pretty mysterious from the beginning. So I have a bunch of formulas. This is my knowledge base. Over time, I accrue formulas. And these formulas carve out a set of models in semantics land. And this formula here, if it's a superset, that means it's entailed by these formulas, right? So I know that this is true given my knowledge, which means that this is kind of a logical consequence of what I know. Okay, so far what we've talked about is taking formulas and doing everything over in semantics land. What I'm going to talk about now is inference rules that are going to allow us to directly operate on the syntax and hopefully get some results that way. Okay, so here is an example of making an inference. So if I say it is raining, and I tell you if it's raining, it's wet, rain implies wet, then what should you be able to conclude? It's wet, right? So I'm going to write this inference rule this way with this kind of fraction looking like thing where there's a set of premises, which is a set of formulas, which I know to be true. And if those things were true, then I can derive a conclusion, which is another formula. This is an instance of a general rule called modus ponens. This says for any propositional symbols P and Q, if I have P and P implies Q in my knowledge base, then that entails Q. Okay? So let's talk about inference rules. Inference. Actually, let me do it over here since I'm going to run out of space otherwise. Okay, so modus ponens is the first thing we're going to talk about. So notice here that if I could do these type of inferences, it's much less work, right? Because it's very localized. All I have to do is look at these three formulas. I don't have to care about all the other formulas or propositional symbols that exist. And going back to this question over here about, what happens if I have new concepts that occur? Well, you can just treat everything as just a new symbol. There's not necessarily a fixed set of symbols that you're working with at any given time. Okay, so this is the example of an inference rule. In general, the idea of an inference rule is that you have rules that say, if I see F1 through Fk, which are formulas, then I can add G. And the key idea, as I mentioned before, is that these inference rules operate directly on the syntax and not on the semantics. So given a bunch of inference rules, I have this kind of meta algorithm that can do logical inference as follows. So I have a set of inference rules, and I'm just going to repeat until there's no changes to a knowledge base. I choose a set of formulas from the knowledge base. If I find a matching rule inside rules that exists, then I simply add G to the knowledge base. Okay? So what the other definition I'm going to make is this idea of derives and proves. So inference rule derives, proves, so I'm going to write KB, and now with a single horizontal line, to mean that from this knowledge base, given a set of inference rules, I can produce F via the rules. Okay? This is in contrast to entailment, which is defined by the relationship between the models of KB and the models of F. Now, this is just a function of mechanically applying a set of rules. Okay, so that's a very, very important distinction. And if you think about it, why is it called proof? So whenever you do a mathematical proof or some sort of logical argument, you're in some sense just doing logical inference, where you have some premises and then you can apply some rule. For example, you can add, multiply both sides of the equation by 2. That's a rule. You can apply it, and you get some other equation which you hope is true as well. Okay, so here's an example. Maybe just for fun, I'll do it over here. Oops. So I can say it is raining, and if I dump that, it gives me my knowledge base. It has rain. If it is raining, it is wet. So if I dump, then I have this is the same as rain implies wet. Okay, just in case you're rusty on your propositional logic, if I have P implies Q, that's the same as not P or Q. Okay. And notice that I have also wet appearing in my knowledge base, because this in the background, it's basically running forward inference to try to derive as many conclusions as it can. Okay, and if I say if it is wet, it is slippery. Again, now I have wet implies slippery, and now I also derive slippery. I also derive rain implies slippery, which is actually, as you'll see, not derivable from modus ponens. So behind the scenes is actually a much more fancy inference algorithm. But the idea here is that you have your knowledge base. You can pick up rain, and rain implies wet, and then you can add wet, and then you pick up wet implies slippery, and then you can add slippery here. And with modus ponens, you can't actually derive some things. You can't derive not wet, which is probably good, because it's not true. And you also can't derive rain implies slippery, which actually is true, but a modus ponens is not powerful enough to derive it. Okay? So the burning question you should have in your head is, okay, I talked about there's two relations between a knowledge base KB and a formula F. There is an entailment relation. And this is really what you want, because this is semantics. You care about meaning. And you also have this KB derives F, which is a syntactic relationship. So what's the connection here? In general, there's no connection, but there's a kind of these concepts that will help us think about the connection. So the semantics, these are things which are, when you look at semantics, you should think about the models implied by the formulas. And syntax is just some set of rules that someone made up. Okay, so how do these relate? Okay, so to understand this, imagine you have a glass. And this glass is, what's inside the glass is formulas. And in particular, it's the formulas which are true. Okay, so this glass is all formulas such that this formula is entailed by the knowledge base. So soundness is a property of a set of rules. And it says, if I apply these rules until the end of time, do I stay within the class? Am I always going to generate formulas which are inside the class, which are semantically valid or entailed? Okay, so soundness is good. Completeness says the kind of the other direction, which says that I am going to generate all the formulas which are true or entailed. I might generate extra stuff, but at least I'll cover everything. That's what it means to be complete. Okay? So the model you should have in your head is you want the truth, the whole truth, and nothing but the truth. Soundness is really about nothing but the truth, and completeness is about the whole truth. Ideally, you would want both. Sometimes you can't have both, so you're going to have to pick your battles. But generally, you want soundness. You can maybe live without completeness, but if you're unsound, that means you're just going to generate erroneous conclusions, which is bad. Whereas if you're incomplete, then maybe you just can't infer certain notions, but at least the things that you do infer, are actually true. Okay, so how do we check soundness? So is modus ponens sound? So remember, there's kind of a rigorous way to do this. And the rigorous way is to look at two formulas. Rain implies wet, and then look at their models. Okay, so rain corresponds to these set of models here. Rain implies wet corresponds to this set. And when I intersect them, that's the set of models which are conveyed by the knowledge base, which is this corner here. And I have to check whether that is a subset of the models of wet. And wet is over here. So this 1, 1 corner is a subset of 1, 1 and 0, 1. So this rule is sound. Remember this, why is this subset the thing I want to check? Because that's just the definition of entailment, right? Okay, so let's do another example. So if someone said it was wet and you know that rain implies wet, can you infer rain? Well, let's just double check this. Okay, so again, what are the models of wet? They're here. One is the models of rain implies wet. They're here, and I intersect them. I get this, these two over here in dark red. And then is that a subset of models of rain? Nope. So this is unsound. Okay. So in general, soundness is actually a fairly easy condition to check, especially in propositional logic. But in higher order logics, it's not as bad. So now completeness is a kind of a different story, which I'm not going to have time to really do full justice in this class. But here's a kind of a example showing modus ponens is incomplete. So for propositional logic. So here we have the knowledge base rain or snow implies wet. And is this entailed, wet? So it's raining, and if I know it's raining or snowing, then it should be wet. How many of you say yes? Yeah, it should be entailed, right? Okay. But what does modus ponens do? Well, all the rules look like this. So clearly you can't actually arrive at this with modus ponens because modus ponens can't reason about or disjunction. Yeah?
Without the rain or snow? But I guess it's saying that it's not possible for it to be not wet given rain.
Is it not? Yeah, because you already know that it's raining. So you should say that, that's why. Yeah. Okay, so this is incomplete. So we can be sad about this. There are two ways you can go to fix this. The first way is we say, okay, propositional logic was too fancy. Question? Yeah.
For the notation, when it says KB equals rain, then comma, rain or snow yields wet, is it implying any type of assignment to rain there? Like, is it saying that it is raining, or is it just saying that we have the variable rain?
Yeah, so the question is, what does this mean? So the knowledge base is a set of formulas. So in this particular formula is rain. And remember, the models of a knowledge base is where the formulas are true. So yes, in this case, it does commit to rain being 1. The models of KB only include the models where rain is 1. Otherwise, this formula would be false. Yeah?
Probability of a model, as in way back before the...
How can we have a probability over a model? So remember that a model is... where did it go? Okay. So remember a model here is just an assignment to a set of proposition symbols or variables, right? So when we talk about Bayesian networks, we're defining a distribution over assignments to all the variables. So here what I'm saying is that assume there is some distribution over complete assignments to random variables, and I can use that to compute probabilistic queries of the formula given knowledge base. Am I answering your question?
Contradict, they can't be in the same knowledge base.
If you have two models that or formulas that contradict, then this intersection is going to be 0. So there exists a set of models. So let me do it this way. So imagine you have these two variables, rain and wet. A Bayesian network might assign a probability 0.1, I should make these sum to 1, what is this, 5? So some distribution over these states, right? And if I have rain, that corresponds to these models. So I can write the probability of rain is 0.2 plus 0.5. So 0.7. Okay. And if I have the probability of wet given rain, this is going to be the probability of the conjunction of these, which is going to be wet and rain, which is here, which is going to be 0.5, divided by the probability of rain, which is 0.7. Does that help? Okay. Oops. Okay, so... Okay. So modus ponens is sound, but it's not complete. So there's two things we can do about this. We can either say propositional logic is too fancy, let's just restrict it so that modus ponens becomes complete with respect to a restricted set of formulas. Or we can use more powerful inference rules. So today, we're going to restrict propositional logic to make it complete. And then next time, we're going to show how a resolution, which is an even more powerful inference rule, can be used to make any arbitrary inferences. And this is what's powering the system that I showed you. Okay, so a few more definitions. So we're going to define propositional logic with horn clauses. Okay, so a definite clause is a propositional formula of the following form. So you have some propositional symbols all conjoined together. Conjoined just means it's added. Implies some other propositional symbol Q. And the intuition of this formula says if P1 through Pk hold, then Q also holds. So here's some examples. Rain and snow implies traffic. Traffic is possible. This is not an example. This is a valid propositional logic formula, but it's not a valid definite clause. Here's also another example. Rain and snow implies traffic or peaceful. Okay, so this is not allowed because only thing allowed on the right hand side of the implication is a single propositional symbol, and there's two things over here. Okay. So a horn clause is a definite clause or a goal clause, which might seem a little bit mysterious, but it's defined as something that P1 through Pk implies false. And the way to think about this is the negation of a conjunction of things, right? Because remember, P implies Q is not P or Q. So this would be not P or true, which is not P in this case. Okay, so now we have these horn clauses. Now remember the inference rule modus ponens. We are going to slightly generalize this to include not just P implies Q, but P1 through Pk implies Q. So you get to match on premises which include formulas which are atomic propositional symbols and a rule that looks like this, and you can derive or prove Q from that. Okay, so as an example, wet and weekday. If you see wet, weekday, wet and weekday implies traffic, those three formulas, then you're able to add traffic. Okay, so here's the claim. So modus ponens is complete with respect to horn clauses for propositional logic. So in other words, what this means is that suppose that the knowledge base contains only horn clauses and that P is some entailed propositional symbol. By the entailed propositional symbol, I mean like KB actually entails P semantically. Then applying modus ponens will derive P. Means that the two relations are equivalent, and you can celebrate because you have both soundness and completeness. Okay, so just a quick example of this. So here, imagine is your knowledge base, and you're asking the question, is there traffic? And remember, because this is a set of only horn clauses, and we're using modus ponens, which is complete, that means entailment is the same as being able to derive it using these rules, this particular rule, and you would do it in the following way. So rain implies wet, gives you wet. Wet, weekday, wet and weekday implies traffic, gives you traffic, and then you're done. Yeah?
First two like rain and weekday, why are those horn clauses?
The question is, why are rain and weekday horn clauses? So if you look at the definition of horn clauses, they're definite clauses. If you look at the definition of definite clauses, they look like this. And k can be 0 here, which means that there's kind of like nothing there. That makes sense. It's a little bit of a, I'm using this notation kind of to exploit this corner case that if you have the and of 0 things, then that's just true. Or you could just say by definition, definite clauses contain propositional symbols. That will do too. Okay, so let me try to give you some intuition why modus ponens and horn clauses. So the way you can think about modus ponens is that it only works with positive information in some sense. There's no branching, either or. It's like every time you see this, you just definitively declare Q to be true. So in your knowledge base, you're just going to build up all these propositional symbols that you know are going to be true. And the only way you can add a new propositional symbol ever is by matching a set of other things which you definitely know to be true and some rule that tells you Q should be true, and then you make Q true, add Q to your knowledge base as well. The problem with propositional more general clauses is if you look at this, rain and snow implies traffic or peaceful. You can't just write down traffic or peaceful or both of them. You have to reason about, well, it could be either one, and that is outside the scope of what modus ponens can do. Yeah?
And peaceful. That way you can say, like, okay, those two are true, so those both have to be true.
Yeah, good question. So what if happens if it were traffic and peaceful? So this is an interesting case where technically it's not a definite clause, but it essentially is. So there's a few subtleties here. So if you have A implies B and C, you can rewrite that. This is exactly the same as having two formulas, A implies B and A implies C, and these are definite clauses. Just like, technically if I give you, hey, what about A, not A or B? It's not a definite clause by the definition, but you can rewrite that as A implies B. So there is slight kind of, you can extend this to say not only definite clauses, but all things which are morally horn clauses, right? Where you can do a little bit of rewriting, and then you get a horn clause, and then you can do your inference. Okay, so resolution is this inference rule that we'll look at next time that allows us to deal with these disjunctions. Okay, so to wrap up, so today we talked about logic. So logic has three pieces. We introduced the syntax. For propositional logic, you have propositional symbols, which you string together into formulas. Over in syntax land, these are given meaning by talking about semantics. And we introduced an idea of a model, which is a particular configuration of world that you can be in. A formula denotes a set of models which are true under that formula. This is given by the interpretation function. Then we looked at entailment, contradiction, and contingency, which are relations between a knowledge base and a new formula that you might pick up. You can either do satisfiability check, or model checking, which tests for satisfiability to solve that, or you can actually do things in syntax land by just operating directly on inference rules. So that's all I have for today, and I'll see you next Monday.